welcome everybody to my presentation. So my presentation is on quantifying rolling contact fatigue in rails. There we go. So first of all, let's talk about how this whole idea began to study this. So TTCI did some work in 2013 where they looked at the RCF performance in a 5-degree curve, where they placed multiple rails, some of them with 0.83% carbon and some of them even up to 1% carbon. And they wanted to find out what's the depth of the cracks and what's the angle of those cracks. And when you line up the results from the gauge phase from point A all the way to point B, you start seeing that there's some trends forming, right? So for the depth, the 1% carbon has a higher depth in cracks than rail that has 0.83% carbon. But then for the angle, all the angles for RCF cracks, they lined up pretty nicely for all those rails. So that sparked the idea to do some of that research in RCF. If you actually look at the visual representation of what the cracks look like for those rails at points X and Y, you see that as the carbon content starts going up, the cracks become more dense and deeper, but the angle stays more or less the same, right? So if you compare 1 to rail 1, 2, and 3, you see that the angle is the same, but those cracks are denser and deeper, and that's even true at point number Y as well. So the main trend is, if you look at this at the schematic, that if you sit at the gauge face corner, the cracks are shallow. And as you sweep to the top of the rail, they become with a steeper angle and deeper. So some of the background. So RCF analysis to date is mostly qualitative. You have people walking out on track and they visually look at the appearance of RCF. They do dye penetrant and they do the magnetic particle, but it's all visual. And based on their experience, by how the RCF looks like visually, they estimate what's the depth of that RCF. There's some quantitative techniques being implemented at this time, and it has to do with eddy current, with magnetic flux, with multi-phase array, with UT. But those methods are not yet perfect, they're not well understood, and this work is to push at least one of those methods forward and to make it more accurate. So the main objective of this work was to find a way to quantify RCF on a global scale and to find an approach that would work for any rail type, whether high, low, any type of curvature, that you could go on track and then grab that rail and then slice it in specific orientations and look at the position of cracks on the railhead, at the length of the cracks, the depth of the cracks, and the angle of those cracks. And then to leverage that information and especially on the crack angle to improve the eddy current method. So to that end, we developed the RCF matrix, and this is one of the layers in that matrix where the vertical axis is the curvature, ranging from 1 to 10 degrees, and the horizontal axis is the MGT level. So if we take 13 rails, for example, as we did in this study, and you place it in this matrix, ranging in curvature from 1 to 5 degrees, and in MGT levels from 300 to about 1,000, that's what this would look like. So usually the population would lie somewhere in this quadrant right there, because rails that have very high curvature usually don't last this long. So this would stay empty. For 13 rails, we did 2 types of slices, one at 90 degrees and one at 45 degrees. As you get more rails into this matrix, you're able to look at different layers in this matrix. So you can start looking at high and low rails, at the rail grade, whether it's standard, intermediate, or premium grade. You can look at the track curvature with variable radius, tonnage, as you see there. The rolling surface condition, whether it's dry, lubricated, top of rail friction modified. At the traffic type, whether it's heavy axle load or transit traffic, at the train speed, so on, and the amounts of grinding. So when we talk about the RCF morphology, we're looking at the position of this RCF on the curve. So where does the RCF start? So as you sweep from this point right there, along the path to the top of the rail, where does the RCF start? That's the position. What's the length of this RCF? What's the maximum depth of this RCF? what's the angle of this RCF to the running surface, and then what's the amount of branching, like for example, branching there. So we're trying to document all of those for 2 different cuts. So we make the traditional cut at 90 degrees, that's the transverse cut, and one cut at 45 degrees, and this cut is orthogonal to the RCF. Now there's a specific reason for doing this type of cut. If you make the 90-degree cut, there's 2 things happening. Number one, the spacing between your RCF layers is fairly high because you're not cutting at the closest distance between the consecutive planes. And then because your cut is fairly short, you don't catch many cracks. When you cut at 45 degree, you're cutting orthogonal to the plane of the cracks. So that angle is 90 degrees right there. So you catch many of those cracks. So the density of your cracks goes up, and also because you're cutting a greater slice, greater distance than this cut, your number of cracks goes up too, right? Now, if you want to compare the 45-degree cut to the 90 plane cut, you need to collapse this position back to 90 degrees. So you just take the component of the position of the initiation point of those cracks, and then you can do a one-to-one comparison. So just to show you visually what this looks like, this is the exact same rail. This is for a 2-degree curve, 390 mgt of traffic. This is cut at 90 degree cut plane. There's not too many cracks. They're fairly long, but the density is not there, right? If you do a 45-degree plane cut for the exact same rail, you catch much more cracks, and then you also build the confidence that you're actually catching the deepest cracks, right? So we did this for 5 rail types here in this study, ranging from tangent to about 5-degree curve, and from 1,000 mgt of traffic to 570 mgt of traffic. This is mostly for the heavy axle load in this case. So you have rails from Canadian National, from Norfolk Southern, from Burlington Northern Santa Fe. So US and Canadian-based heavy axle loads in this case. But you can do this for transit and have a separate matrix for transit as well. And those are the rail origins. So let's take a look at some results. So for the tangent, if you take a look at the crack distribution from the gauge corner to the top of the rail, like I was saying, this is your vertical axis. Your horizontal axis is your position on the railhead, and you see here that your blue dots is your RCL length, your red dots is the RCF depth, and the green dots is the angle of that RCF. So for the tangent cuts, most of the RCF is located right at the gauge face corner. So it's shifted to the left side of the graph there. If you do the etching of this location, you see there's a lot of plastic flow between the layers. As soon as you hit the last layer, this is the undeformed microstructure. So non-isotropic behavior here, and that's isotropic. So that's one of the trends there. When you start doing this for higher angle curvatures like a 1 degree, you see now that the distribution shifts more to the center. The comparison between the 90 plane cut and the 45 plane cut, the angle looks fairly similar. So this builds confidence, because usually when people think of RCF, they see the 2-dimensional slice and they look at this crack, but the crack plane is 3-dimensional. It's like a leaf going into the rail. So as you do multiple slices, you start building better understanding of what this looks like subsurface, right? And then the density of cracks is better here. So you start seeing that. For a 475 degree, the cracks are shifted more to the right even, the density is higher there, and again, the angle comparison. So I invite you to look at the paper that compares even intermediate curvatures with the same type of analysis and has much more detail than what I'm presenting here. If you look at so we also did the micro-hardness profiles at locations, the transverse gauge, TG, and the transverse top of rail, TT, to find out whether the localized plastic flow that's present at the surface and the immediate subsurface is linked with the RCF that's present there. So if you remember for tangent, most of the flow was on the gauge face corner, and that's where the cracking was. And indeed, if you compare the plastic flow here, this plastic flow is greater. So there's more localized plastic flow there, and that layer it develops the RCF. Same trend here, but this here had more distributed RCF, so you start seeing that the plastic flow is more or less uniform. There's a little bit more plastic flow here for the 5-degree curve, okay? Now, so we want to combine this information with eddy current data, and the eddy current right now measures the voltage drop, and that gives you the crack length. That's the measurement, the crack length. But the assumption of the crack angle it's an assumed value. It's not measured value that's done right now. And the result is a crack depth. So something that's measured, something that's assumed, and the result is a crack depth. Well, so the current approach is that if you have 4 different probes and the crack angle is being assumed between 15 and 25 degrees, some of those values are bound not to be accurate because you have an assumed value that's inaccurate. What we want to do is we want to change that assumption to a value that's actually measured. So grab one of our graphs, go to the position, find out where this position is and how it matches with the sensor position, and feed that angle value into the sensor measurement. So now you have a measured crack length, you have a measured crack angle, and you have a more accurate measured crack depth. And do this for all the sensors, and you see that the angle changes from 20 degrees to about 60 degrees, much more variability than 15 to 25 that's assumed right now. So just in conclusion, we're documenting the crack lengths. We're looking at the RCF metrics, the position length, depth angle. This information is useful for people on track, for people who grind, right? Because they get the accurate information. It's also very useful for people who model RCF because they have actual values from rails in service that they can verify their models on. And going forward, we want to leverage this information to get better eddy current measurements. And I want to acknowledge these people here and take any questions.